Now we want to turn our attention away from just measuring concentrations over time to looking at some of the why and how of chemical reactions by talking about collision theory. So everything we've talked about so far has been a reflection of experiment. And then specifically rate laws are kind of the king of describing the reaction or kinetics of a reaction. And they're purely empirical. So that means they're entirely based around reflecting experiment. You do some experimental results and then you figure out what the order is. This is just what the order is, but there's no indication of why. We have orders. Why are there orders? What is an order? What is a rate constant? What do these numbers mean? Everything we've done so far, we've just said, this is what they are. Okay, and so this is reflected in the fact that it's named a rate law. A scientific law is just a summary of a lot of experiments, right? This is what the experiments tell us. We know a lot of experiments have told us that these rate laws exist. There are these constants, and then you multiply the concentrations raised to some exponent. And then we call those orders. But there's no explanation of why. And that all has to come from theories. These are explanations of these facts. Important things about theories is they cannot be proven by experiment, but they can be tested by performing experiments, which is good. And so all the theories that we're going to talk about have been tested before, and we can use them to understand observed phenomenon and to make predictions about other observed phenomenon. And so that's really useful. So collision theory is the main underlying theory that explains the why and how of kinetics. And as the name implies, the idea of collision theory is that molecules have to hit each other in the correct way to react. So this may not seem very groundbreaking, the idea that molecules need to collide. One thing to note is that when collision theory was kind of developed, the developers were kind of selling the fact that molecules existed. So at the time, it was a bit more groundbreaking. But if two molecules are going to react, they have to come into contact with each other. And importantly, with collision theory, they don't just have to hit each other, they have to hit each other correctly. So molecules are constantly colliding with other molecules, but they're not oftentimes undergoing chemical reactions. There are two important prerequisites they have to meet. The molecules have to collide with the correct orientation and with the correct energy. So a lot of times two molecules will collide and nothing happens. Those are unsuccessful collisions, and very, very rarely we get a successful collision where there'd be some sort of change and a chemical reaction will occur. So this baseline idea that we need to have collisions, we can use to explain a lot of things. First off, this is why higher concentrations yield more total collisions. It's not necessarily true that just having more of a reactant makes the reaction go faster, but specifically you need higher concentrations. So if you think about the image on the left, we have, say, a bunch of the light blue is the water molecules, and then the red and the blue are your solute reactants. At a low concentration, there's not really a lot of other things around, and so they don't really collide that frequently. If you increase the concentration, you are increasing the number of reactant molecules per volume. That means the molecules are all closer together on an average sense, and they will therefore collide more frequently. If molecules collide more frequently, that's more opportunities for a reaction to occur, leading to faster rates. So if you want to make a reaction go faster, increasing the concentration leads to more collisions, which means that will lead to a faster rate. So that is why increasing concentrations always leads to faster reactions. So that's good. Collision theory already explains why concentrations show up in your rate law and not total moles. Another thing that we can see is that if you need to have a collision, say your reactant is a solid. Okay, so ideally, if we want a reaction to go faster, we make it into like a liquid. We dissolve things into liquids. That's why we do solution phase chemistry for most things. Sometimes you can't do that. You're dealing with a reactant that is not soluble. So if you have a big chunk of it, like say there's a big old green solid here, if you're going to react these green molecules with the red solute molecules, well, there's not a lot of green molecules that are exposed. So because the surface area of that solid reactant is relatively low, not many molecules are exposed, meaning there are fewer total reactions. If you take that big chunk and you break it up into a lot of little chunks, now there's a lot of exposed surface area. More of those solid molecules are exposed. They can undergo reactions. The reaction will happen a lot faster. More surface area always means more collisions, means more reaction, more processes. We can see this. Iron is extremely flammable. So iron plus oxygen leads to iron 3 oxide. So rust, this is this process. But we use like large pieces of iron for like to hold fire. That's because those are very large chunks of iron. Some of those iron molecules are getting burned. They're oxidizing. You can get rust. That's why you put like protective coats on these pieces of metal. But they're big chunks of iron. They're not really going to react that aggressively because there's relatively few atoms of iron that are exposed. If you take that iron and turn it into a powder, you get a sparkler. So there's other molecules, there's other reactants in there. There's flammable, other kind of burny things in a sparkler. But the sparks you're seeing are coming from iron burning. And it's just iron that's been made into a powder. It's still the exact same metal. You've just changed the shape of the pieces of reactant. There's more of the iron that is exposed. It is all ground up into a very fine powder. Lots of atoms are exposed. So the same like relative number of successful collisions can happen. There's just more collisions with more iron atoms, and they're going to burn a lot more quickly. This also is the reason why a giant chunk of ice melts more slowly. In this case, the collision is just a kind of a one molecule collision. It's just the molecules in the solid ice falling out. Basically, they're leaving the solid and moving into the liquid. They break out of the solid structure. And so if you have more surface area on a smaller piece of ice, that's why you get faster melt, because it's the molecules on the outside that are doing the reaction. The molecules on the inside of this giant chunk of ice, they are freezing cold, right? It's only the molecules on the outside that are exposed to this warm weather that this dude's rocking a t-shirt in that are able to melt, that are actively undergoing those changes. Those molecules in the middle aren't. They're not exposed. It's not possible for them to do this process. So that's why the melt is going to be slow, because only the molecules on the outside are exposed and are able to undergo the process. Molecules on the inside, it's plenty cold on the inside. They're not going to melt. You know, this idea, it may seem, collisions, of course, molecules have to react, but we use this in kind of the most brute force way. If you don't want the iron of your car to rust, cover it in paint. That's why we use paint. That's why we use coats. Sealants do the same thing in wood. That's why they're called sealants. If you have sealants on your teeth, they're doing the same thing. You are preventing chemical reactions from literally just putting a physical barrier in them. So the paint literally just blocks air from reaching the metal. So oxygen in the air is what's doing the corrosion to form rust. You just paint over it. We said that water and salt speeds up the process. What water does is if you get water on the metal, it acts like a solvent. Collisions happen most readily in the liquid phase. If you think about it, you got gas molecules. They're just kind of floating around out here, bouncing around. Say they collide with the metal and then they, would shoot off into another direction. If instead there's water on there and say oxygen got into the water, it would hold it onto the metal. So that would keep it right there. It would hold it right next to the surface, increase the number of collisions, the length of time that the oxygen is next to the metal, more likely that a reaction would occur. Salt is a really big problem. That's why you'll note the rust on this car is coming up from the road because it's salt off the roads. TBD on what salt is doing here. It's making some of those collisions more effective, but it's not necessarily affecting the number of collisions. Whereas water and paint, paint decreases the number of collisions, water increases the number of collisions. More collisions, faster chemistry. All right, another video down, participation 2-1, looking for questions on that. We will see in the next video.